When it is necessary to create a sheet metal cone or cylinder, you must create the profile in that shape from the start. There is no way to completely roll the part into a cylinder from the flat state. Let's start a sketch on the top plane of this new part and use the 3-point arc tool to create the profile of the sheet metal cylinder. I'm using a 3-point arc instead of a circle because the profile must have a gap so that it can be flattened. You can make the gap as small or as large as necessary. Next, I'll use the base flange icon from the sheet metal toolbar to define the sheet metal part. After completing the base flange, you can use the flatten icon and the cylinder will be unfolded into a flat pattern. Because the part is now essentially one giant bend, many of the sheet metal features such as edge flanges cannot be added. You can, however, create cuts. If you wish to create cuts in the flat pattern, remember to use the unfold and fold features. Let's take a look at creating a cone. To do this, I will start with a cone-shaped solid part. I used a revolve feature, but you can use any feature that will result in a cone. Next, I will apply the shell feature in order to make this a thin-walled part. In the Faces to Remove selection window, I will pick the top and bottom faces. I'm almost ready to convert this to sheet metal, but I need to add a cut to this part before it can unfold. A through-all cut using a rectangular sketch works fine for this. As I draw the sketch, however, note that I need to make sure one of the cut sides has a straight edge, so I'll make one rectangular edge coincident with the origin. Now I can convert this into sheet metal by using the Insert Bends feature. In the Fixed Face or Edge selection window, I'll click this edge and click OK. The part can now be unfolded. A lofted bend allows you to create a loft that can be unfolded into a flat pattern. To accomplish this, you must first have 2 sketches created. If you've used the loft feature before, you know you can use more than 2 sketches to create a loft. However, when creating a lofted bend, you are limited to using only 2 sketches. An additional requirement is that these sketches each contain only a single open profile, like I have here. To activate lofted bends, I'll go to the Insert drop-down menu, and in the Sheet Metal section, I'll click Lofted Bends. The Lofted Bends Property Manager appears. The Formed option assumes that no additional facets will be created along a bend, while the Bent manufacturing method assumes that the part will be machined by forcing it to bend at a desired angle and shape. I'll select Formed. To define the lofted bend, I'll select the profiles. When creating formed lofted bends, the sketch profiles need to have smooth connections between the sketch segments. As you can see, I've already broken all the sharp corners, so I'll select the sketch. Next, I'll specify a thickness and click OK. Now the part can be flattened. This resulting part is similar to the cone and cylinder-shaped parts in that I'm limited to what I can do at this point. I can add cuts, fold and unfold the part, but I cannot add most sheet metal features, such as edge flanges. When a lofted bend is manufactured, the deformation of the sheet metal used can be quite drastic. You'll want to keep this in mind so you don't end up with a model of a part that cannot or should not be manufactured. To help you make this decision, SOLIDWORKS has added an analysis tool called Bend Deviation. This tool is used when examining the flat pattern of a lofted bend. So, in order to use it, first click the Flatten icon to see the flat pattern. Now expand the Flat Pattern feature and right-click on the feature called Flatten. Now you can select Bend Deviation from the pop-up menu. In the Property Manager, Bend Deviation will report the changes in surface area of the folded and flat model. You will also see the deviation parameters on each of the flat pattern edges in the graphics area. If you only wish to see the maximum deviation, click the checkbox in the Property Manager. Next, let's take a look at the bent manufacturing method. Using bent lofted bends, you can easily create detailed physical bends between 2 parallel sketch profiles, which can be used to facilitate instructions for press brake manufacturing. Here I have 2 open sketch profiles that I'll use to create a bent lofted bend feature. These sketches are parallel, but non-parallel sketches can also be used to create this feature. I'll go to the Sheet Metal toolbar on the Command Manager and click on the Lofted Bend icon. The Lofted Bends Property Manager appears. The bent manufacturing method assumes that the part will be machined by forcing it to bend at a desired angle and shape. This option also lets you specify the facets to create along the bends. I'll select the circular profile and the right edge of the rectangular profile to generate a preview of the lofted bend. For this feature to work, the profiles must both be open sketches, and no more than 2 profiles can be chosen to create the lofted bend. Also notice the sketch profiles don't need to have smooth connections between the sketch segments, unlike the formed option. The faceting options and facet value group boxes allow you to choose the parameters for how each facet is measured and what numbers are used to define it. The chord tolerance, number of bends, segment length, and segment angle options can all be used individually or in combination with one another. Under Facet Value, there is an option to Refer to Endpoint. When this option is checked in, the active faceting option will take into consideration the points that exist on the ending profile of the loft. In this case, the endpoints are the vertices of the square profile. I'll go ahead and make sure this box is checked for all of the faceting options. The chord tolerance is a measure of the maximum error between a curve and the line that approximates it. This means that if I were to increase this value, you can see that the loft up to the circular profile has less segments to define it and is no longer close to a perfect circle. The number of bends option determines how many segments will appear for each of the bends. I can increase it to add segments or decrease it to remove the segments. The segment length option allows you to specify the length of the bend segments on the profile. Notice that if I increase or decrease the value, that the number of segments changes to accommodate the chosen length. Finally, the segment angle option allows me to define the facets with an angle between the adjacent lines of the segments. Like the other options, I can set this option to any value I like, and the number of segments will update with the chosen angle. Keep in mind that although all 4 of these options are available, they cannot be simultaneously used with each other. Instead, only a single option from this group box can be active at a time, and the preview of that active faceting option is the one that will generate when the loft is complete. I'll choose to define this facet by its number of bends, and set the number to 8. I'll also make sure that Refer to Endpoint is checked on so that segment transitions at sharp corners are taken into account. The faceting options and values set in the Property Manager apply to every bend that's indicated by a pink dot in the preview. To adjust these options for individual bends, I can just click on a corresponding pink dot and use the Faceting Options dialog box that opens to make adjustments. For this particular bend, I'll set the faceting options to Number of Bends and give it a value of 5 so that each segment between a vertex and the related portion of an arc will contain 5 bends. To finish up, I'll go to the Sheet Metal Parameters group box and make sure that the Override Default Parameters option is filled in. Instead of the defaults, I'll make sure that both the thickness and the bend radius are set to a value of 0.8 of a millimeter. I'll click OK, and the Bent Lofted Bend feature is formed. SOLIDWORKS allows you to create your sheet metal designs using the same multi-body design techniques as with regular parts, but there is some added flexibility that makes this particularly useful when working with sheet metal. Oftentimes, designs require several pieces of sheet metal that get assembled together. If you're comfortable using top-down assembly design, then you know how powerful it can be having in-context features that drive the geometry for both pieces of sheet metal. With multi-body sheet metal design, the same power is extended to the part level without the need for any complex in-context file relationships. In this example, I want to create a simple top and bottom cover for an enclosure. I'll create both bodies here in the same SOLIDWORKS part file. I'll get started with a basic sketch for the bottom cover. Give it some dimensions, and create the base flange. Notice in the feature tree, a sheet metal feature has been created along with the base flange and flat pattern. That's all I'll create for now for the bottom cover. For the top cover, I'll start a new base flange on one of the bottom cover's side bends. I'll start a new sketch on it, and I can take advantage of the edges or points on the bottom cover by using sketch relations to define the size of the new geometry. Again, this is similar to top-down assembly design technique, but it keeps things simple by using relations within a single part file. That way, if the bottom cover ever changes size, then this flange for the top cover will update automatically. I'll add a dimension to fully define it, and click on the Base Flange tab icon. Now, if this were to be a simple tab feature in a single body sheet metal part, SOLIDWORKS would absorb the overlapping sketch segment, and this would effectively extend the original flange. But in this case, I want to create a separate body, so I must uncheck the Merge Result option. I'll make sure the new flange is being added to the outside of the original flange, using the Reverse Direction option if necessary, and click OK. When I do, the flange is added, and a couple new items appear in the feature tree. Notice there's a Cut List folder, which lists both sheet metal bodies. Also, notice how there is now a sheet metal folder containing both sheet metal bodies, as well as a flat pattern folder for the flat patterns. Any new bodies or flat patterns that are created will go into these folders. Now, another advantage to designing sheet metal with multiple bodies is that there may be times when you want to work on another area of the design before joining those areas together. In this case, I'll create the next flange for the top cover on the other side. Just as before, I'll start a sketch and use the rectangle tool to take advantage of sketch relations to control the size of the flange based on the existing features. I'll click the Base Flange tab icon, and again uncheck the Merge Result option, so it doesn't add this as a tab to the bottom cover. I'll make sure it's being added to the outside of the bottom cover and click the green check. The flange is added as a new body, and in the feature tree, you can see it listed in the cut list section along with the addition of the third sheet metal and flat pattern features in the folders. The next step is to merge these two flanges for the top cover into a single body. This can be done easily by using an edge flange. All I have to do is click on one of the edges, and to combine it with the other side so that they merge together, there's an end condition for this edge flange that I must use called up to edge and merge. With this option selected, all I have to do is select an edge of the other flange. When I do, you can see a preview of the resulting bend. Something to keep in mind when merging two sheet metal bodies with an edge flange is that both bodies must have the same thickness, since these will both share the same sheet metal feature, and that the edge you select to merge them must be linear and parallel. I'll click OK, and the feature is added, and both side flanges are merged into a single body. Notice in the feature tree, there are only two bodies in the cut list, as well as only two sheet metal and flat pattern features. However, if I expand the second body in the sheet metal folder, you can see that the second body is indented under the first body. The second body retains its own sheet metal parameters, but it's no longer a separate body and is instead controlled by the first body. I can add another edge flange to finish up the enclosure, and this time I'll select one of the edges of the bottom enclosure to extend the flange up to. And SOLIDWORKS will use an up to vertex end condition. The bodies will not be merged unless I were to use an up to edge and merge condition. I can add the edge on the other side to include with this edge flange, and the feature is complete. At this point, it would be simple to add additional tabs, cuts, or other features to each of the bodies, and the enclosure design has all of the built-in references and design intent to behave as expected if design changes are needed. You can also flatten the bodies individually by clicking the flat pattern feature for each in the tree and clicking unsuppress, or by pressing the flatten button on the toolbar. Keep in mind only one body can be flattened at a time, so you'll need to exit the flattened state of one body before you can flatten the other.